available online. You have, where'd it go? There it is. I started a discussion on conic sections.
Okay.
Right? I have a whole video. Today is going to be part 2 of 2.
Okay.
You know? So at the end of class, last week, you would call it part 1 of 2,
Okay.
the introduction to conic sections.
Okay.
One of the things I said on the video, at the very beginning of the video, is like, this is something that ideally you would have been introduced to in pre-calculus, let's say. And then we would be kind of reviewing and going a little deeper.
Right.
But I know that the pre-calculus here didn't cover it at all. So that means that this is the first exposure. And the book moves through it really fast. Like 7.5 in particular has a lot of material. None of it's calculus, by the way. but nonetheless, it's new. Right? So it's gonna, if you're going off the book alone, it's gonna be a very rapid pace.
Okay.
You know? What I did, in short, is I talked about what a conic section is, and very simply, this is an upside down cone,
Right.
right? And if you extend each of the sides like past the tip, it would actually extend it in the opposite side as well. So it's, you might call this a double cone. It has like a top half to it, and bottom half to it.
Right.
What I showed is that every conic section, what's called a conic section, conic meaning cone,
Right.
section meaning it's an intersection of a cone and a plane. So the section is where those two intersect. If I had a plane, right, that just cut through it like this, then the intersection would be a circle.
Right.
And I drew pictures of that. If I tilt the plane just a little bit, like that, then, well, let's tilt it this way just because I'm standing on the right-hand side. Then what you would get is not a circle,
It's an ellipse.
an ellipse, right? And if I tilt the plane a little bit more, then you're going to get a longer and a longer ellipse. But if I tilt the plane so that it's perfectly parallel to this edge of the cone, then you would get a parabola.
So, quick question. It's only a parabola if the parallel to that
Yeah.
slope, because
Yeah.
if not, then it would intersect eventually. The bottom wouldn't have the hyperbola.
So if you were choosing like a plane just randomly, completely randomly, it would be extremely unlikely that you would actually get a circle or a parabola.
Right.
Right? Most of the time you're going to get an ellipse, right? Or if you get a plane that's steeper than the edge of the cone, then that means it'll hit this side of the cone, but that means that down here it's also going to, because it's steeper than this line, it'll hit the bottom half of the cone as well.
Right.
So there'll be 2 branches to the conic section, and that's what we call a hyperbola, right? And those are basically the non-trivial conic sections.
So then, I had to just forget. I'm sorry. Yeah. So okay, I'm sorry. I do that.
Yeah.
So, well, then it doesn't matter, and obviously it does, that where your slice is at to determine how the dimensions of the actual graphic are going.
Yeah, exactly. So even like with an ellipse, whether it intersects here or here,
Right.
it's going to change the ellipse. Whether it's here or here, it's going to change the ellipse. Yeah.
So with a good course of action, you define then the slope of the intersection first.
Yeah, that would be a natural way to go, based on what I've said.
Right.
But the way we're going to go is slightly different. So I'm kind of giving you this. So what I've said is just, it's kind of like one of those more, to kind of know the origin story.
Okay.
Like where it comes from. But we're going to transition into a much more algebraic, analytic, geometric approach to it. In other words, using algebra and equations, right? But yeah, I think I personally, being more of a geometry type of guy, you liking the graphs, would probably like to kind of keep going with it, a little further, and there's classes that do that. But the theory one extracting is more the equations and stuff. So that's it. So all this is just to kind of show you like what what they all have in common, why we study these different shapes together. Because if I didn't say this, and I just said ellipse, hyperbola, parabola, like, okay, like what's so special about those? Why are we studying those all together? You know what I mean? They actually have this, what I think is kind of this interesting sort of origin. If there was a family tree of curves, they come from like this common ancestor.
Right.
So anyway, yeah, and so, especially when you think of parabolas, like the kind of parabolas you've seen is ones that go like this, other ones that go like that, perhaps, and you can flip it and that sort of thing. But yeah, you can even go sideways. We haven't done a whole lot with that, but you can. When you're dealing with ellipses, circles, we'll just think of circles as being special types of ellipses.
Okay.
You know what I mean? Like, you can have them going like this, you can have them going like this, right? Mm-hmm. You can have hyperbolas. Hyperbolas are kind of a little bit trickier. Notice that every parabola has like a vertex.
Right.
Every ellipse has what's called a center. Right. Every hyperbola also has a center. Right. And it usually looks something like this, right? Something like this, perhaps. Or if the center is over here, it might look something like that. One of the defining characteristics of hyperbolas, though, is they have these asymptotes. Notice parabolas don't have an asymptote. Right? Even if you might think the y-axis was an asymptote, but eventually it's going to cross that y-axis. Ellipses clearly have no asymptotes. They're bounded. Right? They stay within a certain region. They're kind of unique among the three for that reason. The hyperbolas, you can see how it has two branches, and each branch is kind of taking off to infinity. But you can see that there's going to be this diagonal asymptote. Okay. There's diagonal lines that you can draw with every hyperbola that the graph is getting closer and closer to. Same thing here, right? Something like this and this. So I should probably fix it so it looks like it's getting closer and closer to the asymptote, not curving. It almost looks like it's curving away, right?
Right.
So that looks a little better. And when we're referring to ellipses and hyperbolas, you can come up with a graph by first drawing a box. A box. Okay, right? I'm waiting for the department to order some other colors. I'm showing another color right now. But you can see how every hyperbola has two vertices. Each of these would be called a vertex. Right? Each of these would be called a vertex. And from there, I can kind of draw this line, right? It goes up to the dotted line. And then from that intersection to that intersection. This would be a perfect rectangle. Right? Likewise here. This. Okay? Every ellipse sits inside of a rectangle. Right? I could draw a similar rectangle around the other one. And when I show you the equations, right, the way we express these is pretty similar, right? So like right here, it's x minus h squared over a squared plus y minus k squared over b squared equaling 1. hk is the center of the ellipse. So if these coordinates are like -3, 1, that means h is equal to -3, y is equal to, k is equal to +1 in that case. Okay. And the a and the b would be, so notice how the a goes with the x, b goes with the y?
Yes.
A is the distance in the x direction. So in this picture, for this particular one, not this one here, but this one, A would be this distance right here.
I'm sorry. Oh, on your equation, that's a plus?
Yeah, that's a plus.
Okay, just want to be sure. And so it's the distance between.
Yeah. And likewise, B is the distance from the center to the edge in the y direction. So with hyperbolas, the form is very similar to the form of an ellipse when you write it out as an equation. Okay. The only difference being you got a minus instead of a plus. See how there's a plus right there? Right. Got a minus right there. And because subtraction is not commutative, you can see how it makes a big difference whether I put the x first or the y first. Over here, it didn't really matter. So I decided to keep associating the b with the y, a with the x. And, but yeah, when the positive term is the x term, that means this is going to have x-intercepts, right? That means it's going to be this one right here. Actually, well, but when the y term comes first, that means it's going to be opening up and down like this instead of side to side. So one way or another, you got to keep them straight, because ultimately, I think the most basic skill, you know, apart from any kind of like clever or tricky problems, right? Most basic two skills, I would say, is if I just draw an arbitrary picture of a hyperbola, can you come up with the equation? Or, and then the second skill is this: if I give you the equation, can you draw the picture? So just like over there, HK is still the center, right? Just like over there, A is a distance from the center to the edge of the box in the x direction. So right here, this distance would be A. And this distance right here would be B, right? And right. When it comes to parabolas, then what I call the center HK over here, that's going to be the vertex over here. Okay. Right. And so like an equation such as this one would be in the form of y minus k equaling 1 over 4p, which I haven't, even in the video from last week, I haven't gotten into yet. It would be of this form, right? Back in pre-calculus, we would have just left, we just call this A, right? So all equations of parabolas fall into one of these two forms. If it's opening up or down, it's going to be where the y is not squared and the x is. If it's opening to the left or to the right, then you're going to be looking at a parabola of this form, where x is not squared, y is squared. And you'll know whether it's opening to the right or the left, depending on whether this factor in front is positive or negative, right?
Okay.
If this is a positive number, then it's going to open up. If it's negative, it's opening down. If this is a positive number here, it's opening to the right. If it's negative, it's opening to the left, right?
Right. Okay. Well, because that should be the inverse of that, right?
Mm-hmm.
So once you just flip it across the XY, the way it's open.
Mm-hmm. So, although it would be more natural to kind of continue our discussion of like imagining planes and stuff like that, and I think that would be actually pretty interesting too, we're focusing more so on the algebra side of things, working with these equations, being able to make the connection between the pictures and the equations, and even using equations to answer questions about the picture. Right? So, yeah, that's the analytic part of analytic geometry. You know, doing it, answering geometry questions with equations. Right? So yeah, that's the idea. And that everything I've said so far is what I said last week, just shorter. Right? What I didn't tell you about is like what does P stand for. I also didn't talk about the focus and the directrix. And that's basically what I wanted to finish talking about. I've been kind of flip-flopping back and forth also, because like I said, the book goes into pretty thorough and complete depth on this discussion. And there's some topics that I was decided to just skip over. Yeah, so, but anyways, like, yeah, so been flip-flopping back and forth on how much I want to hold you responsible for. But like, for example, you know, these are all these like conic sections are defined with respect to the x and y axes. But what I just erased was this cone, and we're imagining a plane. There was no axes to be spoken of. Right? The whole idea of a conic section is actually independent of the coordinate system. Right?
Okay.
In other words, I could speak of an ellipse like this. Right?
Right.
And the equation for this ellipse will not fall into this form.
Okay.
So what I've just shown you here is very much only when the the longer between A and B, whichever one's longer, that's called the major axis. The shorter of the two, that's called the minor axis.
Right.
Same thing here. This is only what I just written here is only true when the major and minor axes are parallel to the x and y axes. You see? Same thing with a parabola. I don't have a major minor axis, but I do have a line of symmetry, which notice is parallel to the x-axis. Here, the line of symmetry is parallel to the y-axis. But if I want to write the equation of a parabola that looks like this, you know, like I can't do it with this. But nonetheless, these are conic sections. They are the result of a plane intersected with a double cone. So one of the sections I would like to cover that section, which is ambitious, but there's a section that shows you how to handle this, and the complete discussion would be found in linear algebra, which is not a prerequisite for this course, nor is this a course in linear algebra. It is a class that's offered at Pierce College and any other community college.
Right.
So you can take that, and the teacher may or may not decide to go into this, but what you do is you learn how to handle it, how to handle it in this situation. Because really, the way you handle it is you got to talk about another type of transformation that we haven't done a whole lot with, which is a rotation transformation. Right. We've talked about reflections, we've talked about stretches, we've talked about shifts, but one transformation we've done very, very little of is rotations. And this is a type of rotation, especially if I want to rotate it by like 35 degrees or something like that. How do I do that? So linear algebra would be one place where that question is answered. But so that means that the discussion that's given in the book, they do tell you how to handle this, but it's in a very formulaic way. They give you formulas you just use without explanation.
Plug and play.
Yeah, which is good news. It means just plug and play, like you said. but you won't have the satisfaction of knowing why this formulas work. Does that make sense?
Yes.
So, yeah. Anyway, so I think in that, if you just treat it as plug and play, then those might actually be the easiest questions I could ask. Because I won't be requiring any insight into it.
Right.
Anyway, yeah, we have our hands plenty full just wrestling with trying to, because there's a lot of ideas coming together here. And the final thing I want to go into, which I didn't go into last week, is understanding the idea of the focus and the directrix. Another way of looking at these things, different from like thinking as a cone, is you can talk about the focus and the directrix. Every single one of these conic sections has a focus and a directrix. So for example, one of the defining properties of a parabola is that it has a focus. The focus is typically inside, somewhere inside the parabola, let's say about there. And the directrix is a line. It's a line that's outside the parabola, say like right here. What all the points in the parabola have in common, okay, I'll call this F, call this focus and directrix. What all the points in the parabola have in common is that it's literally the set of all points that are equidistant from the focus and directrix. In other words, you pick any point on the graph, actually it doesn't even look like the way I've drawn it. If I draw this to scale, then the distance from here to that point is equal to the distance from here to that line.
Okay.
Right? So in other words,
but D's not, the directrix is not arbitrary. It's a defined line.
yeah. So for example, like I'll just draw a diagonal line like this.
Okay.
Call this the directrix. Pick any point that's not on the line, right? So this is a line, by the way. It's not a line segment, so I'll put arrows on there to know that it's a line. Pick any point that's not on the line, say this one. I'll call this the focus, right? And we can speak of the set of all points that are equidistant, meaning the same distance, from the point and its line. So for example, there's one that's really easy, right? If you measure the shortest distance from this point to this line and pick the midpoint, right here, the distance to the focus is equal to the distance to the directrix.
Right.
So this is one point that's on the parabola that's determined by the focus and the directrix. But there's lots of other ones, right? For example, if you imagine measuring the distance that the focus is from the directrix and drawing like a square out of it, so that this distance is equal to this distance.
Right.
This is also a point on the parabola. If I draw another square over here, so that this distance is equal to that distance, this is also a point that's on the parabola. There's 3 points now that are on the parabola. Right. And there's other ones in between, right? Like for example, I estimate there'd be one about right here, right? And what I'm imagining in my mind is this distance right here and this distance right here, so that distance is equal to that distance. And that's just one of many, right? If you start plotting all the points that are equidistant from the focus and the directrix, right, you'll start to get a bunch of points that look like that, right? And in fact, as you get even further away, notice I could go like this, but then it might be something like that, so that this distance equals that distance, right? So this would also be a point on the parabola. And if you just, there's infinitely many points that are equidistant from this point in that line. And if you trace them out, start to look like that. What all these points have in common, if you measure this distance and this distance, it's always the same. Right? So that's an interesting property of the parabola. All right. Furthermore, this distance right here, the distance from the vertex to the focus, which of course is also the same as the distance from the vertex to the directrix.
Right.
That is P.
So for VSATs, very small aperture satellites,
Sure, yeah.
the parabola is based off, or the antenna is based off that.
Yeah, yeah. Yeah, so there's a lot of, when it comes to conic sections, there's so many connections to be made.
Right.
Like on one hand, I'm talking about like these cones, but then like this looks like it's something that, like what in the world does this have to do with cones? And yet, this is something simultaneously true. And then thirdly, which what you're mentioning, is if you were to pick, if this was like, a radio transmitter,
Right.
and so that it's sending the signal out, emanating in all directions. If the signal goes this way, one of the properties of the parabola is that it will reflect in a direction that's parallel to the line of symmetry. Even right here, if you have a radio wave that's coming this way and it bounces off the wall of the parabola, it's going to also reflect, but because it's right here, it'll also reflect in a line that's parallel to the line of symmetry. Even over here, as the radio wave is going this way, when it bounces off, it'll go parallel to the line of symmetry. And so it takes this signal that's emanating in all directions and actually redirects them to all go in the same direction. So that's a much more focused signal that will cover a much greater distance. So yeah, a lot of really interesting properties to be had from there. And so you can see how being able to locate the focus, if this is like the type of application you want, it's really crucial that you know exactly where the focus is.
Right.
If you're going to put this broadcasting point like a centimeter to the left or a centimeter to the right, or even a centimeter further away, then it won't be parallel anymore. So yeah, so we want to be able to. So I think when it comes to like being able to locate the focus in the directrix, it's pretty easy in this case actually. If you have this in terms of 1 over 4p, right? Because now if I give you an equation such as x plus 3 equals 1 over negative 12 times y minus 4 squared.
Okay.
Well, now I can see that this is going to be a parabola because the y squared is either opening to the right or the left, depending on whether this is negative or not. And it is negative, so that means it's opening to the left. So I'm thinking of a parabola with an x-coordinate where the vertex is at negative 3, and positive 4. So there's the vertex, I'll call it V. I know it's opening to the left, and I would basically just kind of loosely just sort of do something like this, right? But in reality, it could be very skinny, it could be very fat, right? So, but I can get a better idea of what it's going to look like if I can identify the focus in the directrix.
Right.
Now, from this, I can see that negative 1 over 12 is the same thing as negative 1 over 4 times 3.
Right.
That means that P equals 3.
Right.
So, if I was to go, so from here I can go, so this is at what, negative 3 and 4? That means that the coordinates of the focus
is at negative 6 and 4.
Yeah.
And the direction is the y-axis.
Mm-hmm. Yeah. So the equation, what's the equation of the y-axis?
Y equals 0.
Mm-hmm. So x equals 0.
Yes. Yes. X equals
Yeah.
0.
So the focus is at -6 and 4. The directrix is x equaling 0. This is a set of all points on the plane with an x coordinate 0. So with that in mind, I can see that I can now see that I actually drew this much too skinny.
Yeah.
I can see now because I can quickly pick up these 1, 2, 3 points. The vertex is right here in the midpoint between the focus and the directrix.
Right.
But I can quickly pick up 2 more points.
So it would be the. I'm sorry. So 3, 3, and 3. So -6, 7.
More. See, this is a square, right?
Right.
That means this distance equals this distance.
Right.
2 equals 3, and that's actually 6.
Yeah. So 6, -6, 10.
Yeah. That's probably going to be up here.
Wow.
And at -6.
-2? No.
Yeah.
6. Yeah, -2.
Yep. Should have left myself more room. So maybe about right here.
Okay.
So now I can see, now I can come up with a much more scale sketch. I can see that it's going to look something like that.
Right.
So knowing that distance P is going to help you come up with the picture. It's going to help you to identify where the focus directrix is. So if I give you the equation, well, then you can see what P is, but from that you got to be able to come up with the coordinates of the focus and the directrix, right? As well as the picture itself. And if I give you the picture, can you figure out what P is? You know, that kind of question can be asked in many different ways. So that's a tricky one. In these 2 pictures, we don't really have this distance P, right? What we do have is what these all have, with ellipses, you do have a focus in the directrix. With a hyperbola, you also have a focus in the directrix. Okay. But the relationship is different. You see, because with these, this distance equals that distance.
Right.
In other words, the ratio is 1. We have a name for it. It's called eccentricity. Eccentricity is the ratio.
Decentricity?
Eccentricity. With an E. I'm gonna. I always get it mixed up which number goes on top and which one goes on the bottom. So I'm looking it up right now.
Let's do that. So I can be given an eclipse.
Ellipse.
I'm sorry.
Mm-hmm.
There's eclipse coming, just in case you guys didn't know.
Oh, okay.
I can be given an ellipse and draw a hyperbola from that ellipse, right?
Sure. Yeah. Mm-hmm.
And vice versa.
Yep.
So the space in between the hyperbolas.
Mm-hmm. Yeah, okay. Eccentricity. Yeah, actually, the eccentricity comes in handy because all these. But part of what I'm omitting is the when is you can all do this all in polar coordinates as well. You can parameterize all these, and that's actually probably maybe I should because it's like a natural extension of what we've been doing, right? But we already have our hands pretty full right now. So the eccentricity E of a conic section is defined to be the distance from any point on the conic section to its focus divided by, okay, so it's this distance to the focus divided by this distance to the directrix.
This distance to the focus divided by.
Mm-hmm. So if I denote the focus with capital F,
Okay.
I'll denote the directrix as with a lowercase d.
Okay.
And if I pick an arbitrary point on the parabola, right, then I'll call this, I don't want to call it P, it might be confused with that one. I'll just call it like, I'll call it Z uppercase Z, right? The eccentricity is the distance from F to Z. These are points that, writing points next to each other, that denotes the distance.
Okay.
Divided by the distance from Z to D. So what all these points have in common is that this distance always equals that distance.
Yes.
And that's why the eccentricity for a parabola is 1. Every parabola has the same eccentricity.
Right.
So all parabolas have an eccentricity of 1. But when the eccentricity is less than 1, then you get a ellipse. And when the eccentricity is greater than 1, that's when you get a hyperbola. And knowing the eccentricity, so the eccentricity is a great thing to know because based on how big it is, you immediately know whether it's a parabola, an ellipse, or a hyperbola. And I think this is probably the natural direction you were going in based on your earlier question. You were saying, like, I'm going to look at the intersection of a plane with a cone, right? It seems like I'd want to be able to get at the slope or the incline of that plane, right? And the eccentricity is kind of like that. Notice this is when the plane was parallel to the edge of that cone. The edge of that cone, by the way, had a slope of 1. You know what I mean? And then, but when the plane was kind of tilted, but not a whole lot so, that's when it was an ellipse.
That's the one, yeah. Okay.
And then when the slope was really steep, like bigger than 1, that's when we got the hyperbola.
Okay.
So again, lots of connections to be made, right? Lots of like, all interconnected, different ways of looking at these things. So pretty deep stuff. And but yeah, so like, and so one thing you notice is that if I come back to this ellipse, every ellipse has a center. It has like the length of the semi-minor axis, the length of the semi-major axis. Semi because it's just half of the length of this rectangle.
Right.
And but we also have, every ellipse has 2 foci. Right? 2 foci. Foci is the plural of focus. Right? They generally are about right here,